Let's go ahead and get started. Okay, so last time we left off on covalent bonds, and remember that's going to be where we share our electrons. So molecular compounds are going to form when we share electrons among atoms. Okay, that's the definition of it. And so atoms are two or more nonmetals typically are going to share their electrons. They're going to form a covalent bond. That's a good enough definition for this course. If you want to talk about more, there was actually a discovery that was published 2 weeks ago that they found an entirely new type of bonding. And so there's stuff happening. But good enough for this course, okay? So the valence electrons is going to be shared by nonmetal atoms to achieve stability. Remember the stuff we were talking about where everything wants to be noble-like for its electron configuration? That's where this starts coming in. So a molecule is going to form when two or more atoms share electrons. Literally, that's why you have a molecule. It's because two or more atoms are sharing electrons. Now they're going to be moving around together, right? And so you have fused them together. By the way, do not refer to it as fusion. I just read an article from what is supposed to be some sort of science journal, and they were talking about how things were being fused together to make ammonia, which is not correct. Remember the nuclear stuff? That's fusion. The other ones, exactly. They're just molecules. They're just a reaction.
Because you can actually separate them.
Yeah. It's totally fucked up. So the hydrogen molecule, H2, this is going to form. As you have two hydrogens moving towards each other, what's going to happen is they have their nuclei and they have their electrons, right? And so when they get near enough to each other, their electrons are going to start being attracted. Hey, I need to not be trying to talk over 5 groups. This is not going to be okay. I'm going to lose my voice eventually. Okay, now, so when we bring these atoms near each other, what's going to happen is that the electrons are going to start getting attracted to the nuclei, right? Because the electrons are negative, the nuclei are positive. And so eventually they're going to get close enough where they start sharing the electrons. And this is what we refer to as a covalent bond if it shares the electrons. Okay? Now, is there a minimum distance they can't go past? What happens if the nuclei start getting near each other? They're going to repel, right? Yeah, and that's that minimum distance. Once those nuclei start getting too close to each other, they're going to repel each other. Okay? All right, so this is actually a demonstration of this. Here we have two hydrogens coming together. Notice that right now they're so far apart, they don't experience any repulsion or attraction, right? As they come closer and closer, what's going to happen is first, we're actually going to have the electrons repel each other. Now, when you touch things, what are you actually experiencing? Are your atoms actually coming in contact with the atoms of the object you're touching?
No. There's repulsion, there's a slight resistance. If your atoms were actually coming into direct contact with it, you'd just be able to mix together and phase through it. Your hand would fuse with the desk. But no matter how hard you push, that's not going to happen.
You'd form covalent bonds. If you actually touched atoms, you'd form covalent bonds. And then your hand would be bound to the desk. And so what's happening is exactly, your electrons are repelling the electrons of the object you're touching.
I wonder what that would actually feel like, come to think of it.
Yeah, it'd be problematic. You could actually experience that a little bit if you have a reaction happening on your hand, but I wouldn't really recommend it. Yeah. Bit like super glue, I guess, but much stronger. Now, the next thing that's going to happen here is once we get past the electrons repelling each other, then what can start happening is the electrons are going to start being attracted to the nuclei. And that mutual attraction between these electrons and these nuclei of the hydrogens is going to pull them together the rest of the way. Okay? And that's going to form what we refer to as bonds. Now keep in mind, bonds are not little sticks between two nuclei. Bonds are literally just two magnetic fields holding on to electrons. Anybody ever seen those magnetic the plates that they put down, like the colorful iron sand stuff on them, and it like wavers and moves around? You guys have never seen those demos? They are on desks sometimes. Yeah, of people that have way too much money and room on their desk. But you can also see this to some degree in various. Anybody ever seen the magnetic deals where they put like the balls in the little spin deal, and then it starts spinning faster and faster? Okay, those are all applications of dual magnetic fields acting on an object, in case you're wondering. And so in reality, these atoms, these electrons are sort of moving around and popping all over the place here. Okay. So a molecule is going to be represented by a Lewis structure. This is going to be where we'll have the valence electrons of all the atoms. They're going to rearrange to give us what is referred to as an octet. For the first 3 periods, octet's actually an okay way of calling that. Okay? Oct meaning what? 8. Yeah, so octet, everything's going to have 8. The exception to that is hydrogen. Hydrogen can only have 2. Okay? Now, if you ever want to do anything beyond what an octet will give you, if you ever want to have a more coherent framework to work with, everything wants to be noble-like. Okay? So everything's going to move to its nearest noble gas.
So is helium an octet also? Since it's already got a full
Nope.
valence?
It's 2 electrons. It's referred to as an octet, but that first period can only have 2 electrons.
Okay, that's
Yeah.
what I wasn't sure.
Yeah. That's why I don't like the octet naming. Honestly, I hate the octet naming. It's a really, really, really incoherent way of naming it. And it works on periods 2 and 3. And the reason it works on periods 2 and 3 is because there are only 8 spaces on periods 2 and 3, right?
Yeah, because after that it goes to like 18 or something.
Yeah.
And you get on the shelf.
Yeah, and you can have extra octet. But we're not really going to get into all that. We just need a fairly limited application of this so that we can get to basically organic molecules and understand why organic molecules look like they do. And so in reality, what we're doing is see carbon, nitrogen, oxygen right there. That's like 90% of what we want. Right there. We just need to figure out how to do molecules of carbon, nitrogen, and oxygen. Okay? That's 90% of what this class is going to be. We don't really have to worry about much more. So, the number of electrons of nonmetal atoms shares and the number of covalent bonds it forms are usually going to equal to the number of electrons it needs to achieve a noble gas-like arrangement. On periods 2 and 3, this is going to be 8, meaning octet, right? The shared electrons are going to be what are known as bonding pairs. They can be shown as 2 dots, but I am going to highly recommend that you do not try to show them as 2 dots on your pages. Okay? Did I go through why I recommend that?
About how they're connected with the carbon and everything.
Yeah, you are going to come into my office and you're going to go, Dr. Clausen, my notes make no sense. I don't understand them. What is going on? Okay? That's literally what happens to about a third of the class if they try that. All right? So, bonds. Don't forget, though, that you can actually show them as 2 dots between. Okay? That is also a bond if somebody does that digitally. Right? Notice even when I try to draw it up here is not exactly the perfect thing to do, right? It's kind of a mess. But digitally it works actually pretty well. Because digitally everything can be aligned, right? So, single line between the atoms or 2 dots directly between the atoms. These represent bonds. Okay? And those are bonding pairs of electrons. Non-bonding pairs of electrons are going to be referred to as lone pairs. Literally, they are pairs of electrons that don't have another atom with them. Okay? And so they are on a lone atom, and they are a pair of electrons. And these are placed on the outside away from the other atom. And so here we see examples of both. Here we have two fluorines coming together to make a single bond. Okay? See the two electrons in between? That's a bonding pair. See these ones on the outside that are not between the two fluorines? Those are lone pairs. Okay? And so each fluorine has 3 lone pairs and 1 bonding pair, right? That means they have 8 electrons total, that being an octet, isn't it? Everybody see that okay?
The lone pairs are like on top.
Yeah, there are these things. Okay, by the way, see this a pair of electrons that are being shared? They are sharing them so they can both have 8 electrons associated with them, right? And so they can have a noble-like configuration. Okay. Okay, so the elements hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine, these all actually exist as what's called diatomic molecules. So if you were to get a sample of, say, iron, or you were to get a sample of, say, carbon, okay, they are not going to necessarily form into pairs. But if you get a sample of nitrogen, oxygen, fluorine, any of these diatomics, they're going to always pair up and make bonds whenever you get a sample. You can't actually find them by themselves. Okay? Is that making sense so far? And so those always bond to themselves and make these diatomics. Okay, so this is a Lewis structure right here. So right here we have the Lewis symbol for carbon. We have the Lewis symbol for hydrogen. And what we do with these is we always just write the symbol from the periodic table and we fill it around with electrons. We do it one at a time at first. And then when we need to double them up, we will double them up. Okay? So hydrogen has just 1, and carbon has 4 equally spaced around it.
So you want us to do the lines, we just like put one line? Is that like how we do it?
Yeah, for a bond. Yeah. This would be what it would look like when you do the Lewis structure. This is how I would recommend writing it on the page. Okay? If you need to do the other, this works fine for digitally. Okay?
Okay.
Like, you can see it's actually not that hard to do digitally.
So one line equals $2?
It does. Yep. This would be the equivalent to this. Okay. And those are bonding pairs of electrons. Okay. All right. Notice what is true about this. The number of valence electrons for each of the atoms has to be the same as the number of valence electrons for the entire molecule. Okay? Because things do not get created nor destroyed. The same number has to be true in both cases. What we see here is to be noble-like configurations. The carbon needs 8 electrons associated with it, right? So 4 bonds. Each bond is 2 electrons, right? And that's 8 electrons around it. So we fulfilled its octet, haven't we? Hydrogen, on the other hand, to be noble-like, only needs 2 electrons. And so the hydrogen, each hydrogen just gets 1 bond. Each bond has 2 electrons, doesn't it? Yeah. And so we just arrange everything into configurations that are going to give them octets. Now, there's going to be a very tight set of rules I'm going to give you that you'll be able to do these structures perfectly every single time as long as you follow the rules. Okay? Some professors or teachers, if you've ever done this before, give you kind of a loosey-goosey rules and try to get you to do stuff before they're supposed to be done. And you'll have the ability to fail. I don't give you the ability to fail. That's just not how I do things. So, these are some different Lewis structures here for common molecules, like ethane, ammonia, and water, right here. You may appreciate those. So a double bond, what is a double bond going to be?
2 pairs of electrons are shared.
You got it. 2 shared pairs of electrons. Literally double, meaning 2, right? So it's 2 bonds in one place. Okay? Triple bond's going to be what? 3 bonding pairs of electrons, exactly. 3 bonds. Okay? And so again, these are something that we'll put in when we need to complete our octets. So we're going to draw the structure for carbon dioxide, CO2, in which the central atom is carbon. Now notice I've told you the central atom here, but there's actually an easy way to figure that out. Okay? What you always do is you look at your atoms, and the thing that needs the most connections, that needs the most electrons to be an octet, that's the thing in the middle. Okay? So for example, carbon is further away from the noble gas than oxygen is, isn't it?
Yes.
So carbon ends up in the middle.
So will they have double bonds?
You will, yeah. But let's do the steps. Okay. Okay, so first thing we need to do is these things need to connect together somehow, right? It's not a molecule if they don't connect together. And so the first thing we do is we take the carbon, draw it, and we take the oxygens and we put those around it. We know carbon has to be in the middle, doesn't it? Okay. The next thing we do is we go ahead and put 1 bond to each of these. Okay. We do that because everything needs to be connected. Okay. So if we don't have a lot of stuff that makes it more complex, we can just automatically go, well, everything has to be bonded. Okay, so what I want you to do, though, is this is the true start of everything, is we're going to look at our periodic table, and we're going to go, I have carbon, I have 2 oxygens, don't I? Okay. Carbon has how many valence electrons? 4. Yeah, we look at that periodic table. That's that 4A number. Or the other way we can do it is we can count from the left, right? And we can go 4 steps in. That's 4 electrons in its valence shell. Okay, how many electrons does it have? Yeah, you got me. The oxygen has 6 electrons, right? And there's how many oxygens? 2. Got it. So times 2. And so my total valence electrons I need to account for here, just like I'm doing a checkbook or something, right? I'm balancing out how many I have so I know how many I can spend, right? Is, yep, you got it. 2 times 6, 12, plus 4, 16. Okay. Okay. So we need to spend 16 ultimately. Okay. How many have we spent so far? 4, exactly. And so we go minus 4, right? We have 12 remaining. Okay. So the next step you're going to do, once you have everything connected together, okay?
Why 4 again?
These are 2 each. The bonds are 2 each.
Wait.
See, we have 2 bonds there.
Yeah.
Each bond is 2 electrons. So 2 times 2 is 4.
Okay. Yeah.
Okay, so the next thing we're going to do, and this is where my methodology differs from what a lot of you might have been taught if you've been taught anything, okay, is you fill in all the outer atoms first, okay? So we're just going to put lone pairs on the outer atoms until we use up all of our electrons, if we do, okay? So the outer atoms want how many electrons here? Oxygen wants 8, right? And so I'm going to go and put, can you guys see those okay? Okay, let me see if I can get this. Yeah. Okay, is that okay if I do that? You guys can tell those are electrons? Okay. Okay, so I put 2 as a lone pair, right? Now I'm up to 4. How many more do I need? 4 more. Yeah, so I'm going to put 2 more lone pairs, right? Okay. And so now I have 8 electrons around my oxygen. Can everybody say it okay? Okay, and that one's full. Okay, the next thing I'm going to do here is I'm going to do the same for the other oxygen, so that I can get 2 full oxygens. Now I've filled everything up that's around my center, right? Don't touch the center yet. Okay. Okay, so how many electrons have I accounted for now?
16.
Yeah, I've actually accounted for all 16, haven't I? Okay. Okay, so I don't have any more electrons. I can't go in here and fill in the middle one with electron pairs, can I? I'm out. Okay. But I don't have octets for everything, do I? So the next thing I need to do is if I had more electrons, I'd fill in the center. Okay? I don't though, so that step can't be done. Okay? Or rather, it's done. Any extra electrons got spent, right? Okay. Yeah, we're good. Okay, and so the next thing I'm going to do here is I need to fill in that carbon, don't I? I have to get it to an octet. Okay? And so what I'm going to do is I'm going to take lone pairs from the outside, and I'm going to bring them into bonds so they're shared. Okay? Okay. So I take that lone pair, I bring it into a bond. Everybody okay with that so far? Okay. And that gives me 6, doesn't it? And then I go ahead and go to the other side, and I take another lone pair and bring it into a bond. Okay. And that gives me 8 total, doesn't it? Okay. And so that right there is actually my valid Lewis structure. Okay. Anybody have any questions?
Yeah, which lone pair, how do we decide which lone pair to get rid of?
Okay, so this is actually where we're going to get more rules later. But the best way to do it is all things equal. Just take them and bring them in based on the number of electrons you typically want. So like if we look up at oxygen here, you can also take that number of steps to a noble gas and go, that's the number of bonds it normally wants. Does that make sense? This is actually referred to as formal charge if you do this correctly. But I'm giving you a quick way of doing it here. Okay? Before we actually get into the nitty-gritty. Yeah. Did that make sense? Okay. Okay. So like carbon typically is going to end up with 4 bonds. Oxygen typically is going to end up with 2 bonds. Like a fluorine or chlorine, it typically ends up with 1 bond. Okay? And that's just the number of steps to a noble.
Why did you take those and put them in the middle? That's where I'm confused.
So these right here are not being shared, right? And I need to share them so that carbon can get up to 8.
Because carbon has to have 8 also.
Exactly.
Well, and it only has 4, right?
It only had 4.
Okay. Oh, so a line is 2 dots.
A line is 2 dots.
Okay.
Yep. A line is 2 dots, 2 bonding electrons. Okay. Any more questions? We good so far? Fantastic. Okay. That right there, by the way, that's going to get you like 80% of Lewis structures, what I just did. Okay? And it's going to get you 80% of Lewis structures perfectly every time. Okay? Because I've given you almost all the rules, so we're actually pretty much done. All right. And you can see there. All right. So let's talk a bit about exceptions to the octet rule. This is where the rest of those come in. Now, the reason I said 80% of rules we already figured out is because does anybody know how much the mass of the solar system we've already accounted for going up to the second period? It's the mid 90% of the mass of the universe, of the solar system. Like, we've accounted for almost everything in the solar system. That's why you're made of carbon, oxygen, nitrogen, right? It's because it's available. Okay? So, the hydrogen requires just 2 electrons to form a noble gas arrangement. Is everybody okay with that?
So it needs only 2 dots, right?
It does. Yep. And again, if you forget for whatever reason, how can you figure that out?
Can you write it so we can see what it like looks like on there? 'Cause I'm like a little confused how it's gonna look.
I mean, we've already done that several times. That's with all these.
Oh, so just one. Okay.
Yeah.
Got it.
It just has one bond to it.
Okay.
Yeah.
You can tell from how far it is from the noble gases.
Exactly.
It means a full electron.
Exactly. So if you just go to period 1 and look at that period, you can see that there's only 2 things on it. That's telling you that it can only fit 2 electrons on period 1. So hydrogen can only have 2 electrons. Okay, so the nonmetals P, S, Cl, Br, and I, these can form compounds with 10 or 12 valence electrons. You'll notice those are all on period 3. Can you see it okay? Okay, that seems like a violation, doesn't it? Things are weird. Did anybody remember my d orbitals when I talked about those? Ooh. What period do they actually get made, those d orbitals? 3, yeah. So you actually have, basically think of it this way. On period 2, you only have 8 spots available, okay? On period 3, you have 8 good spots available, but we have another 10 spots that we don't like to use. So if we get more electrons, we can fit them in, okay? And that's why all of these are what are referred to as an extra octet. They can have 10 or 12 valence electrons. It's possible, okay? This only happens on period 3 nonmetals. The S atom has an octet in many compounds. The SF6, there are going to be 12 valence electrons, 6 bonds to that sulfur atom. And again, that's because that has that extra octet. It's on period 3. It can fit those extra electrons in. And fluorine's the big bully that always takes electrons from everybody, right? And so it's going to pull those electrons away. Okay, so these are the electronegativity values for our representative elements in groups 1A to group 7A. This is how you determine how well an atom holds on to electron density. Okay, so if it has a small electronegativity, it means it loses its electrons very easily. If it has a large electronegativity, it's going to take and pull those electrons very well. Okay, you'll notice that fluorine, which is the top right, has the largest electronegativity. The smallest electronegativities are going to be as you go down and to the left. Okay, and that's that same thing we talked about before. So remember that the metals lose their electrons very easily. Those are down on the left. The nonmetals, they typically keep their electrons, don't they? And those are up and to the right. Okay? And this is why. Notice what does not have values. See the noble gases, how they don't have values? Okay. So electronegativity is how well it pulls electrons in a bond. Okay? The noble gases don't bond. Yeah. And so they don't have a measurement of how well they would bond. Because they just don't bond. Right? You can kind of think as this is like a measurement of how well you arm wrestle, and the nobles are like, psh, arm wrestling. Not going to take part in that. Okay. So electronegativity, again, this is the value of an element, indicates the attraction of an atom for the shared electrons in a bond, or how well it pulls those electrons towards it. It increases again from the left to right across the period on a periodic table. It increases from the bottom to the top of the periodic table. Going up the periodic table is usually your largest changes. Going from left to right are smaller changes, typically. Going to be high for nonmetals. Fluorine is going to be the highest on the periodic table. It's low for metals, and that's why they're always losing their electrons and making things like ionic bonds. Okay? This was why the ionic bonds were happening. And this is why covalent bonds are happening. Covalent bonds happen when the electronegativities are similar. Ionic bonds happen when you have a large difference. And so one loses the electron to the other. Okay. So let's talk about the polarity of the bonds. So we have these sharing electrons, right? But we know not everything shares equally, does it? Okay? You get a cake, you put it out. Does everybody get an equal amount? Basically never, right? Like, almost never. And so, how do we tell this? Well, we tell this because some people don't eat a lot, some people eat a lot, right? Okay? So think of the electronegativities. We have things that pull electrons very well. We have things that don't pull electrons as well, right? So if you have a moderate difference in those electronegativities, what's going to happen is the electrons will still be shared, but one is going to pull the electrons more towards it than the other. Okay? Okay. Is that making sense? Okay. Okay. Anybody ever seen a tug of war? Okay. What happens when the groups are mostly equal?
The flag says
Yeah, when they're perfectly equal, the flag stays in the middle, right? When they're equal-ish, but not quite, the flag moves off the middle, doesn't it?
yeah, just barely.
Yeah. And so that's what you're seeing with a polar bond, okay? When you get a polar covalent bond, the electrons are going to spend more time around one atom than the other. That's because it pulls them better than the other one does, okay? A good example of this is these are hydrogens. They're the exact same strength, and so they pull exactly equally, and the flag stays in the middle, right? The electrons spend about the same time around both of them, okay? And so there's no poles to that. There's no positive end, there's no negative end, okay? When we look at this, the chlorine here has a considerably higher electronegativity than the hydrogen. Can you see that? Yeah. So the chlorine pulls electrons much better than the hydrogen, okay? And what's going to happen is those electrons are going to spend a lot more time around the chlorine. Electrons are negative, so that makes the chlorine negative.
So fluorine always pulls.
It does, yeah. Yeah, it pulls electrons very well. And there's not really anything that's going to equal it. Yeah. It almost always makes a polar bond. You have to really look to try to make a non-polar bond with chlorine, or fluorine. Though fluorine plus fluorine would be non-polar. So this is referred to as poles, by the way. That's why we're calling it polar, like the poles of a magnet, right? So this hydrogen literally has a slightly positive charge. This chlorine, on the other hand, has a slightly negative charge. Okay? This is referred to as a dipole, meaning two poles. Okay. Okay, so let's look at nonpolar covalent bonds real quick. This is going to occur typically between nonmetals. It's going to be an equal or very close to equal sharing of electrons between two bonding atoms. It's going to have a very small electronegativity difference. That's why it has basically equal sharing. Okay? You have two atoms that are about the same strength, or perfectly the same strength. And here we see some different examples. These are all nonpolar covalent bonds. And that's because their difference in electronegativity is very small. So they hold the electrons essentially equally. Polar covalent bonds, on the other hand, are going to have a moderate difference in electronegativity. So this is going to occur between typically two nonmetal atoms. It's going to be an unequal sharing of electrons, but it is still a sharing, right? We're still sharing the electrons. One doesn't take it from the other. It's just not equally sharing. Okay? And this is, again, a moderate electronegativity reference. And these are some of those differences right there. And so these are polar covalent bonds. Okay, what do you think is going to happen if you have a large difference in electronegativity? What happens when one of the groups in a tug of war just completely outclasses the other? Yeah, they just pull the whole rope towards them. The entire other group just goes flying, and it doesn't have any equality at all, right? And that's called ionic bonding, isn't it? Where we just lose the electron to the other one. Okay? And so those don't make covalent bonds. they make ionic bonds. So polar covalent bonds, again, are going to become more polar as your difference in electronegativity increases. The separation of your charges in a polar bond is going to be called a dipole. That's where you have two poles, exactly like a magnet. You have a positive end and a negative end. Okay. There's several different ways of designating this. We can use the lowercase Greek letter delta with a positive or negative sign. Does anybody know why we use a lower Greek letter delta? Does anybody know what the capital delta looks like? Anybody ever seen that? That's capital delta. Okay? And that means whole changes. When we have partial changes, we use the lowercase delta. That means partial change. Okay? And so literally we're saying partial positive, partial negative here. And that's the two ends of a dipole, meaning the two ends of a magnet. Positive end, negative end, right? The other way we can designate this, and probably the one that will work best for you, because it'll be easier for you to deal with, is we put a plus sign where it's positive, and then we put an arrow towards where it's negative. Okay? That means the same thing. It's just a different symbol for it. Okay. So again, when we have a large difference in electronegativity, typically a difference of 1.8 or greater, greater than 1.8, excuse me, then this is going to be a wholesale electron transfer. That is referred to as an ionic bond. They are not sharing the electrons anymore. The electron has transferred. Okay. There is no dipole to this. There's a whole charge difference. Okay. Because electron has moved. Right. Typically, this is going to actually happen between metal and non-metal ions. That's where you'd see this the most often. Okay, so that difference in electronegativity values for the two atoms, these can be used to predict the type of chemical bond. It's not perfect, but for us in this course, it's good enough, okay? That difference between 0 and 0.4 is typically going to be a nonpolar covalent bond. It means a covalent bond where essentially the two electrons are being shared essentially evenly, okay? The 0.5 to 1.8 is going to be a polar covalent bond. That's where they're unequally shared. One is going to have the electrons more than the other. And then a 1.9 to 3.3, this is an ionic bond. Technically, it could get higher. It just pull more electron density. Okay? But 3.3 is basically the highest you're going to get with just the atoms. All right, so this is a summary of these things in a chart, and this actually shows you kind of what they would look like with the molecule. Can everybody see it okay? Okay, see how these are even? The electrons are basically even around them. These ones here, the electrons getting pulled away from this one, right? Over to here. Okay. And here they're just completely separated, aren't they? Because you got positive, you got negative. They're not sharing. Okay, so this is the different types of bonds and showing you different examples of them. And so you can see here, these are actually our metal plus a non-metal ionic bonding that we'd been talking about before, right? And we started the naming with that because that one's the easiest to name. And then we went ahead and we went to these things, which are where they start sharing, right? Those were those covalent bonds. Okay. Oh, I'm out of time, aren't I? No? Okay. Okay. Oh, okay. Okay. That must have been previous. All right, so use the electronegativity difference to identify the type of bond, nonpolar covalent, polar covalent, or ionic, between the following. This will be a quiz, so get ready to do that. Okay. And what I'm going to have you do is tell me the polar covalent ones first, right? So you guys ready? to go on to the next. Do you guys have those? An idea of how you do it? There's the QR. Okay, everybody go with the QR code?
Not yet.
Okay. You can go to slido.com and type in that code, by the way, if you ever can't get the QR to work for you.
Can you go back to the
I can. Everybody got that? Okay. Okay, and so these were the ones. So polar covalent is going to be our first one that we're going to do. So you need to figure out which ones are polar covalent, which ones are covalent, which ones non-polar covalent, and which ones are ionic.
Can you remind us real quick on the difference between non-polar and polar again?
Non-polar is going to be they share them evenly. They have a very small difference in electronegativities.
Non
Polar are going to be where they don't share them evenly. They have a larger difference, a moderate difference in electronegativity.
so non-polar is even and polar equals uneven.
Exactly. Yeah. And you can think of it as a spectrum, by the way.
We're doing non-polar first.
Huh?
We're doing non-polar.
We're doing polar.
Polar.
Yep. You can think of them as a spectrum, by the way. So here they're evenly shared. They're about the same strength. As you get more and more difference, you go towards more and more ionic. Okay?
it's metal and non-metal.
Exactly. Yeah. Okay. Everybody ready?
Yes.
Let's go. Dun 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 dun
Yeah, mine
dun
isn't
dun
showing.
dun.
Okay.
Oh.
Oh, wait, are we supposed to select multiple?
Yeah, you can select multiple. Any of them that are polar covalent.
Yep, I ran out.
Yeah, work on a.
So, yes. Okay.
Good job.
And that came as potassium.
It is. So that's a metal and a non-metal,
Potassium's
and that would be ionic. Yeah. Potassium's. You can look up there, by the way. K is all the way to the left. Okay, folks, you ready for the next one? Ionic bonds. Ready? Go. Which ones are ionic?
Chlorine's a metal, right?
Chlorine's a non-metal. Okay.
Wait, that one didn't have. I thought that one that you select multiple.
You can. In this one, you didn't need to.
But I tried to select both the top and the bottom, but it wouldn't let me.
Oh, okay.
That one was only a single.
Okay. Well, you didn't need to. Probably why I didn't make it. Yeah. Yeah, that one's only potassium is the only metal on there. Hydrogen is a non-metal despite the fact that it's over towards the left. That's because it has a higher electronegativity. And yeah, that is weird. They actually used to have it on the periodic table as a grayed out one right above fluorine. So there were periodic tables where it would be in two places, and that would show you the duality of hydrogen. Yeah. Okay. So let's use the electronegativity difference to identify the type of bond, nonpolar covalent, polar covalent, or ionic, between these following ones. This right here is those difference in electronegativities. See those okay?
Will you give us that one? If this is on the test, would you give us like?
I mean, you don't need them.
Okay.
Like, honestly speaking, for most of these questions, I'm not going to give you something close enough that'll be meaningful. Yeah.
So it's just gonna be like potassium is and nitrogen are non-metal and metal. So we just need to know that's ionic.
Yeah, so that's ionic. And then the other ones, they have a pretty big difference in their position. And so you can go, okay, those are going to be polar.
But we don't have to say which one. It's like, oh, it's polar. Hydrogen is polar to this, or vice versa.
Yeah, it's not going to be so close that it's like I put a hydrogen next to something that has almost the same electronegativity.
Okay.
And it's like you have to get 0.4 versus 0.5.
Okay.
Question. So ionic is non-metal and a metal, and then polar is.
Where they have a fairly significant difference, a moderate difference between their electronegativities. Or another way of saying that is if you look at the nonmetals, both covalent types, polar and nonpolar, are both nonmetal and nonmetal. Okay?
So if those are next to each other, that would be polar if they're like closer to each other, right?
So if they're towards the top right, those differences are a bit higher. And so those ones are going to be ones where they're typically going to be a polar covalent. If they're the exact same thing, they have to be nonpolar because they have to be equal.
Okay.
Okay? And that's typically the trick I play, so you don't need a table, is I give you ones that are the exact same ones for nonpolars. And then I give you ones that are not the same ones and up on the top right for the polar ones. Yeah. And that way I never get a situation where you're like, it's 0.4.
And I'm noticing the polar ones, they're
Uh-huh.
like the same, like both non-metals or both.
Yes, all covalent ones are nonmetal with a nonmetal.
But the polars are metal, right?
All of them.
Okay.
So nonpolar covalent and polar covalent are both nonmetal with nonmetal. If it's metal with a nonmetal, then that's going to be ionic almost across the board.
Yes.
Yeah. Okay. Okay. All right. Are we good? Fantastic. Okay. So the shapes of the molecules. So here we have methane. And you may have noticed that here's its Lewis structure, but it doesn't really tell you what it looks like, does it? It just tells you what's connected to what. Because it's all in 2 dimensions. Obviously, objects in the real world are not 2-dimensional, right? So, what do we do here? Well, we have an atom in the middle here that's connected to 4 different things. Those things do not want to be in the same space, do they? Because they have electrons. They're going to repel each other. Okay? And so what happens with all of these, and you could do this with balloons, by the way, if you want to try it out. If you were to take a bunch of balloons and tie them into a single point in the middle. So you take 4 items, tie them in a single point in the middle, and what are they going to do? They're going to spread out in all directions so that they're as far apart as they can get, right? Okay. Do you know what arrangement is as far apart as it can get? Camera tripod, isn't it? Everybody seen a camera tripod?
Yes.
Looks a bit like this, doesn't it? Yeah. The reason for that is because it wants to be as spread apart as possible. It wants the highest height it can get while also having the sturdiest bases it can get, right? And that's the most spread out of a 4-membered object. Okay? And so that's what this does. It'll have angles between the bonds of 109 degrees. And this is referred to as tetrahedral. That's actually what that shape would be, right? Can everybody see that's a tetrahedron right there?
So if it's like a tripod, it's a tetrahedron.
It is, yeah. And that's what happens whenever you have 4 groups around a center that are trying to spread out as much as possible. Okay? Okay, and so this theory that allows you to take and figure out these shapes based on how many groups are around a central point, this theory is valence shell electron pair repulsion, or VESPR. So VESPR theory. So it's going to describe the orientation of electron groups around a central atom. By the way, the naming for this is a little weird. If you look in different books and different sources, these names are considerably different. Like there's 5 different ones that could be. Okay? You're going to catch me oftentimes referring to these as domains, which is actually a better word for them. So I will often say, instead of electron group, I will often say electron domain. Okay? Okay. Which is actually better terminology. But I'm going to try to stay consistent with your book so you don't get as confused. Okay? Okay, so the states that the electron groups or domains are arranged as far apart as possible around a central atom. It states that the specific shape of a molecule is going to be determined by the number of atoms attached to the central atom. And this actually has to be true for most of these things. Think of it a bit like this. If you have two things that repel each other, what's going to happen every time you have them attached near each other? They're going to repel each other, be as far apart as they can get, right? Yeah. And so it's funny, but you can actually take balloons for all the Vespers, and you can literally just put as many balloons as you have different domains around a central point, and that'll always give you the structure. So if you ever want to demonstrate this for yourself, just take some balloons, fill them up, put them next to each other, okay? Or go to a store and get filled balloons. Either way. So in the molecule CO2, we're going to have two electron groups that are placed around the central atom. The central atom being carbon. The repulsion is going to be minimized by placing those two groups on opposite sides of the atom. This shape is called linear because literally it makes the shape of a line, right? Okay. And so these right here, see the double bond here and double bond here? Those are what I refer to as electron domains. Your book refers to them as electron groups. Okay? Anybody know why the domains is better terminology? What does domain mean? Domain is an area you have control of. So the area the electrons have control of is being separated as much as possible, right? Yeah. Okay, what if you have three domains around a central point? What shape would that be? It's going to look like a triangle. Yep, you got it. This is referred to specifically as trigonal planar. Okay? Literally a triangle in a plane. Okay? So trigonal planar. Okay, what's going to happen if you have three groups that are all around a central point, but one of those groups is not atoms? Ooh. So what if one of these groups was no longer atoms?
I was gonna say before, is it okay to write it as either the Lewis structure or the other one, or does it matter?
So the Lewis structure won't give you any idea of the three-dimensional structure of it. This one is the rearrangement of the Lewis structure to show you the three-dimensional structure of it. Yeah, that's all that is. But that's actually where you get these domains from. So once you make your Lewis structure, you would then count up the number of electron domains around it, and that's how you determine the Vesper structure. Okay, so this is a case here where we actually have a lone pair. Everybody see that lone pair okay? Okay, now lone pairs are going to take up space. There are electrons, they're going to repel the other bonds, right? So they're going to take up space still. But they are not actually part of the molecule, are they? They don't have an atom on the other side. Okay? So this is where we need a bit more terminology than your to understand this, if we want to understand it, than your book necessarily gave. Okay, so this right here, there's two different types of terminologies. There is the electron geometry. So what geometry do the electrons take up? Okay, and then there's going to be the molecular geometry. The molecular geometry is the shape the atoms take up. Is that making sense so far? Okay. Okay, so we look at our Lewis structure. There's one group here, right? There's a double bond, which is a single group. Okay? All bonding sets are a single group. So a single bond is a single group, a double bond is a single group, a triple bond is a single group. Lone pairs are also going to be a single group for the counting up the electron geometry. Okay? And that's always the first one you want to start with. So we look at these. There are three different groups for the electron geometry. There's a single bond, a double bond, and lone pair, right? That's three. Okay, so what's the maximum separation for three groups? That's trigonal planar, right? Is everybody okay with that so far? Okay. Okay, so we go ahead and arrange those like a trigonal planar. Can everybody see the triangle that we've made? Yeah, because the lone pair is up here, right? Okay. Okay, so what's the shape of the molecule then? Well, the lone pair doesn't have any atoms on the other side, right? So the molecule is going to have what's referred to as a bent shape. Literally, it be bent. Right? Can everybody see the bent shape? Fantastic. That's the molecular geometry. The geometry of the atoms. Okay. Okay, so let's go ahead and look at something that's tetrahedral again. Here we have the carbon in the middle. And this has its different hydrogens around it. Everybody see that okay? Okay, so carbon has 4 groups around it. Is everybody okay with my 4 groups around it? 4 single bonds, 4 groups. Okay. Okay, maximum separation for 4 groups is tetrahedral, right? So the electron geometry around carbon is tetrahedral. The molecular geometry around carbon is the same thing because we don't have any lone pairs. Okay. Okay, let's look at another tetrahedral, but now we have a lone pair. Okay. So again, this nitrogen here has 1 lone pair, 1 bond, another bond, and another bond, right? That's 4 groups around it, or 4 domains. Okay, maximum separation of 4 groups or domains is tetrahedral again, right? So the electron geometry around this nitrogen is tetrahedral. Okay. What would be the atoms, though? They're not tetrahedral, are they? Yeah, because there'd be no top object for the atoms, right? The molecule. So this is going to be trigonal pyramidal. See how it looks like a little pyramid when you look at just the atoms? Okay. So electron geometry, tetrahedral. Molecular geometry, trigonal pyramidal. Okay. Okay. Let's look at water. Anybody ever wondered why water makes snowflakes? You ever notice that water freezes and it makes these really interesting shapes that look a bit like that? No? You guys have never seen snowflakes under a microscope? No? Okay, that's sad. Go look up snowflakes under a microscope. It's actually quite beautiful. Or freezing water under a microscope. You can get YouTube videos where they do some cool stuff with it. Make it look very pretty. And it makes on this hexagonal shape. Okay? This is actually going to be why that happens. Okay, so this is the Lewis structure for water. It again has 4 groups around it. Can everybody see it okay? Okay, 2 lone pairs, 2 bonds, right? 4 groups around it. Okay, so 4 groups around it means its electron geometry is tetrahedral, right? Okay, but 2 of those groups are going to be electron lone pairs, aren't they? And so the molecular geometry is bent. Can everybody see that bent shape right there? Okay. Notice if I take bent shapes, by the way, and I put them together, the sort of shapes I get are very reminiscent of what I'd cut out for a snowflake, right?
Yeah.
That's why it's the bent shape actually creates the snowflake shape when you repeat that shape over and over and over. There. Okay, this is actually a summary of the different electron groups. Notice it here has the bonding and lone pair broken apart. And then it tells you the geometries. And it gives you little examples. Okay? That's a handy table as you practice these. So go ahead and do your homework with that. And then what you want to do is try to do it without the table. Then refer back to the table when you get stuck. Okay? And go, oh my goodness, I don't understand this. Okay. How much time do I have left? Okay. Okay. Well, I'm doing pretty good then. Okay. So we're going to go ahead and do a problem. Everybody ready for a problem? Dun, dun, dun. This one won't have a quiz for now because I want practice first, okay? Okay, so we do H2S. All right, so the first thing we need to do is we need to get the Lewis structure together. Okay, what's the Lewis structure going to look like? Yeah, sulfur's going to be in the middle. Okay, and then how many electrons do we have to account for? Yeah, so sulfur is, how many electrons does sulfur have in its valence shell? 6, very good. And then the hydrogens each have what?
1.
Yeah, there's 2 of them times 1. Okay, and so our total number of electrons we have to account for is 8. All right, so we go ahead and draw in our hydrogens surrounding our sulfur, right? Sulfur being in the middle. We're going to put bonds from the hydrogens to the sulfurs. Everybody okay with that so far? Okay. Okay, now, do I need any more electrons on those hydrogens? No, they're full, aren't they? Yeah. So all my electrons are going to go ahead, all my remaining electrons, they're going to go on that sulfur, aren't they? Yeah. And so how many electrons do I have left? 4. And so I go ahead and put 4 electrons on the sulfur. Everybody okay with that?
So, why did you put 4 on there? Because I'm confused. Each side, the lines are like 2, correct?
Yeah. So we had used up 4.
Okay, that makes sense. Okay.
And we had 4 remaining.
Yes.
And then we used up the last 4 on the middle.
Okay, that makes sense.
And so what we do next is we check, does everything have its quote-unquote octet or noble-like configuration, right? Okay, sulfur, 8. We're good. Hydrogen, 2, right? Yeah, we're good. Okay. And that's a valid Lewis structure. So we completed it. Woo!
Question, why does sulfur have to have 8?
Because that's the noble-like configuration, or another way of saying that that's an octet. So if you look, so first off, there's the, because everything on the second and third period should have 8 electrons at least, which is the octet rule. The other way, if you forget that, is to look up at the period, and you see the period sulfur's on has 8 things on it. And so that's how many valence electrons you need to be noble-like on period 3.
4 is what turns to 18, right?
Yeah, 4 is the one that turns 18, though there's actually quite a few things that you can do with the octet rule still then.
Okay.
You can kind of just ignore the d orbitals because they're far apart energy-wise. Yeah. But anyways, that's a more complex topic. Take more chemistry if you want to learn about that.
Is it organic?
That's actually general chemistry, like later general chemistry, and then a little bit of inorganic chemistry. Yeah. Yeah. Okay, so we get the Lewis structure. What's the next step? We need to use Vesper, don't we?
Yeah.
Okay. So how many domains are around that sulfur? There's 2 bonds, right? And then 2 lone pairs. So that's 4 domains, right? 2 and 2. Okay.
Whatever's around it is how many domains, basically.
Yeah. Yeah. Just don't forget that double and triple bonds are just 1 domain. Okay. Okay, so you have 4 different domains around there. So what's the maximum separation for 4 objects?
So it's
Tetrahedral, exactly. That'll be the electron geometry, right?
Yeah.
What would be the molecular geometry then? Okay. So that would look something like this, right?
That's what we said.
does look like sad face. But the molecular geometry would be bent. Yeah. So it'd be bent. Okay? Okay. Okay. Ooh, we still have 4 more minutes. Dang. Okay, one more Vesper. So state the number of electron groups and lone pairs. Use the Vesper theory to determine the shape of the following molecules or ions as tetrahedral, trigonal pyramidal, or bent. Okay, so what is PF3 going to be? Anybody ready? Okay. Yep.
Have to do the dot thing first.
The Lewis model.
Yeah, you have to do the Lewis structure. And there is actually somewhat of a shortcut to these.
Yeah, because you can see the F3, so there's
Yeah.
going to be around.
Yeah.
Just try to-
Yep. So yeah, you can total these. The other way you can do these, if you get comfortable with this, is the number of steps to a noble is actually also equivalent to the number of bonds things want. So like the P, for example, 3 steps to a noble. The F, 1 step to a noble. So typically the phosphorus is going to want 3 bonds. The fluorine, on the other hand, wants 1. And then you just need to fill things in with their electrons for lone pairs.
And so that would have 3 domains.
That would have 4 domains because you're going to end up with a lone pair.
So you're right.
Anyways, that's a shortcut once you get comfortable. Until you get comfortable, do it the methodology that I gave you. You can never screw up.
Challenge accepted.
Yeah. Oh no, if you follow my rules. And if you need to refresh those rules, by the way, I have videos on YouTube of me going through multiple problems on that and going through all the rules again. Okay? Okay. And I go through a pretty extensive number of problems, more than I could have went through in here. Okay?
Hopefully you go over the homework problems.
I do actually go over homework problems sometimes.
Specific. Okay.
Yeah. Yeah. There's a few that are almost the exact same or the same. All right. Okay, I'll go ahead and call that a day. You guys can do this at home, and then come in and tell me if you get it right, okay?